Now, there is something called Z here that is analogous to resistor here. The Z goes by the name impedance. Thing is, now any of this, instead of resistance, if you use impedance in these circuits, you can again do series parallel. This is like a resistor for circuits that have RLC elements. You can do series parallel, voltage division, current division, bridge circuits, all of that can now be handled. So all this work if you use impedance instead of resistance. So now you thought you only learned a small part of electrical circuits, but that small part of electrical circuits can actually let you deal with all linear elements, RLC elements. It's very, very, very powerful. We dealt with this. We have learned this. Learning that, going here is just, you just need one tool that is complex. Recap some basics of complex numbers. Now, let's start something very, very. So you have a complex number plus 2j. I'm going to use j to mean this, okay? Now your j is the square root of minus 1. This is what we typically write as I. So we'll write this. This is a complex number. First thing. So now can anyone tell me what is modulus of z? So while I do that, let's also show this. This is typical to show complex numbers in a 2D plane. Okay, you show the real part of the complex number here and then imaginary part of the complex number here. So this is real of z, this is imaginary of z. The number is the real, this is 1, and then imaginary, this is 2 units. So the number is over here. This is your z, 1 plus 2j. So that's the z of interest. Okay, notice the real part happened to be 1, imaginary part happened to be 2. Okay, this most of you know. Just square root of a square plus b square. So what we are, mod z is essentially this length. Mod z is this length, okay? So we know how to measure length of anything. So mod z is in this case square root of 1 square plus 2 square. It's the length of that hypotenuse. Wherever it is, it's just square of these two numbers. That happens to be square root of 5. Okay, fine. And this most of you know, right? All of you are answering, right? Anyone? We are at it. So what we found is a length. Anyone tell me what is this theta that it makes with this axis, real axis? Okay, notice. So you know the going to be this is a right triangle. Right, from the right triangle you can easily get. This is theta, that is also fairly easy. Notice inverse imaginary component y by x. We typically write your z as x plus j times y. Okay, yj or jy, either is fine. One and the same. Okay, so this is the imaginary part by real part. In this case, this happens to be, let's calculate that. How much is this? Tan inverse of 2, tan inverse of 2, that is 63.43 degrees. This also most of you know. Okay, so for a simple complex number, okay, your absolute value is this. So given this, you can write this in what is referred to as a polar form or exponential form. Okay. Now you can also write this as notice z is 1 plus 2j is the length into e power j 63.43 degrees. This is the exponential form. This is, you can write the angle goes over here, e power j theta. The absolute values goes over here. Sometimes, if you use the Euler's identity, this will be root 5 into cos 63.43 degrees plus j into root 5 sin 63.3 degrees. So there are three ways to write this. Most of you know this. So this is good for addition, subtraction, and trigonometric relations. Sometimes if you're dealing with oscillatory things, this is easy to see what is going on here. For multiplication, division, product, square root, and all that, this form is used. Right? Now let's slightly step up the gear. Now my z1 is 1 plus 2j. This is my first complex number. z2 is, let's say, 3 minus. This is my second complex number. Now I need a couple of things. Okay. So first, let's make sure all of you again know the basics. What is z1 plus z2? Can give this in Cartesian form. Yeah, just add the real components together, imaginary components together. You'll get it. So this is 4 j. 4 plus 1j, that is 4 minus j. Okay. So this is most of you know z1 minus z2. This is minus 2 plus 3j. Right? So you do real and real and then imaginary and imaginary. We have already used this. Now let's say what is z1 into z2? What is this? Multiplication, there are at least two ways to do this. Give me an answer. So one is, you can directly take this. This is method 1. Substitute the numbers, that is 1 plus 2j, 3 minus j. Do product-wise multiplication. That should give you, notice, this into that, okay, and then this into this. Those four things, right? So 1 into 3, 1 into minus j, plus 2j into 3, that is 6j. And then j square happen to be minus 2j square. So know that j is square root of minus 1. So j square is minus 1. Simplify this. How much is this? And I use the j square in this multiplication. Okay, at least I'll highlight one of them. There, 2j into minus j, you have to use this. Okay, so now all of you are giving this. Suppose plus 1 Z2. This case is square is -1. So -2 into -1 is +2. So that is 5 plus 5j. Careful, j square is -1. What is the method 2? Method 2, you could do to convert to exponential. Powers add up, the amplitudes get multiplied. You can do that. And yeah, see, again, this is the point of this is, first of all, make sure that these are all sub steps. Okay, steps in actual gate question. And often gate students don't understand gate question or gate solution because they don't understand a step or two. So we deal with the steps separately and then we deal with the gate question separately. So mistakes do happen. Few silly things do happen. Only thing is, so try to minimize it the second and third time. That's the only thing. In fact, the idea purpose of this session is to bring out subtle things that you might be wondering about. Okay, so this is this. So we are done with Z1, Z2. Now the final thing, let's also do this. Let me write down our numbers. I suppose Z1, what did I say? This is 1 plus 2j, 3 minus j. Let's do a loss calculation. This time we'll have to do Z1 by Z. Tell me how you would do this. So what we are looking for is 1 plus 2j divided by minus j. How do you do this? Vector division is not defined. Complex number division is defined. So you can do this division. Yeah, one is you could take this road. It's going to be, this is the 2. Okay. This is R1 by R2. The amplitudes gets divided power j theta 1 minus theta 2. The division becomes the angles get divided. Division shows up here, division shows up here. Also method 1. Okay, this is simple numbers. We'll do method 1. Either is fine. This is rationalize it. Rationalize it, and right now the problem is you have a complex number in the denominator. Somehow, if you can remove that, make it a this is make denominator real. Not do a footwork, make it that into a real number. Make denominator into real. Do you do that? You have to multiply by real. So most of you are wondering, okay, how do we do that? So here, this is where the thing comes here. Notice if you do a plus JB, if you take this number and if you multiply by A minus JB, this is A square minus B square. But this is technically this is A square plus minus J square B square. Which is this? For any complex number, if you do A plus JB into A minus JB, this A square minus of JB square. Right? So that I'm going to write that as square minus J square B square. What do you get? That's correct. So most of you went to that step, but let's just make sure that this is clear. Okay, so A square minus J square, but minus J square is plus 1. This term is plus 1. J square is minus 1. Minus of J square is plus 1. So what you get as A square plus B square. Let's pause for a moment and notice this. Okay, Z is plus JB. You consider Z star, you just change the negative there. Change the sign of the imaginary number. Okay, then Z star, real number. If you multiply Z and Z star, A square plus B square, purely real. Just that this happens to be amplitude of Z is not, so amplitude of Z is square root of A square plus B square. Not only that, this happens to be take amplitude of Z, square of that. So this gives you now a quick way to make the denominator real. So multiply and divide by the complex conjugate of the denominator. Your denominator is now real. Multiplied and divided it. So net on a net, there is no change. Okay, so let's go continue that problem. So what we have here is 1 plus 2j by 1 minus 3j. Sorry, 3 minus j, right? So we're going to do is multiply and divide by the complex conjugate. On a whole, there is no change. But with this, the denominator becomes a real number. That's also fairly easy to write. The denominator, now this is 9 square plus 1. 3 square plus 1. Square plus 1 square. It's now fairly easy. And then what is the numerator? Can we tell me what the numerator is? Same thing works. 3 plus j plus 6j minus 2. This is, suppose 1 by 10. Denominator is 1 by 10 into, can we simplify this 1 plus 7j, suppose? This is 1 plus 7j by 10. The final answer would be 0.1 plus 0.7j. That is fine. 1 plus 7j by 10 is fine. Real part is 0.1, imaginary part is 0.7. So at least, what have to take this for granted from now onwards. All of you can add and subtract complex numbers, multiply complex numbers, then and then you could also divide with complex numbers. Okay, at least the bare minimum, all of you could do this. Okay, now these circuits. So in fact, this is, let's compare and contrast. You have resistive circuits. In this sign, now I am going to talk about RLC circuits. Circuits can have a resistor, inductor, capacitor. Here for resistive circuit, you have this resistance resistance R, right? Then you had things like, series parallel, then voltage division, voltage and division. Then actually even delta Y holds good, but let's skip delta Y. Bridge circuit. These are all we are used to, right? Balanced, unbalanced bridge. We have seen all of that. Now there is something called Z here that is analogous to resistor here. The Z goes by the name impedance. Thing is, now any of this with instead of resistance, if you use impedance in these circuits, you can again do series parallel. This is like a resistor for circuits that have RLC elements. You can do series parallel, voltage division, current division, bridge circuits, all of that can now be handled. So all this work if you use impedance instead of resistance. So now you thought you only learned a small part of electrical circuits, but that small part of electrical circuits can actually let you deal with all linear elements, RLC elements. It's very, very, very powerful. We dealt with this. We have learned this. Learning that, going here is just, you just need one tool that is complex, which is what I just, told you, right? So all this work, very powerful. Impedance instead of resistance. So this very powerful generalization. full tool. Okay, involve some complex numbers. We'll look at one or two examples and then you get started at that today. The first thing is, so Z, what is this impedance for this? So let's do impedances. Okay, in English this is complex resistance. It's still resistance, but it's complex. This is essentially V by R. Resistance is voltage by current. But still, this is voltage by current, but this is complex. That is involves complex number and function of frequency. It depends on now relation between voltage and current depends on what frequency you are working with. Frequency F is there. I'm going to put W. For R, draw the three elements. You got your R, got your capacitor, got your inductor. Right. So the units for this is farad, SI, which means using that you don't have to worry a lot about it. This is unit for this is Henry. The unit for this is ohm. Okay. So this is just, I'm going to in fact write the impedances. Okay. Impedance for a resistor happens to be R. So let me write this down. This is C farad. This 2 farads, 3 farads, 1 microfarad, something like that. And this is L henries. Henry is a unit. And this is R ohms analogously. Right? So impedance for a resistor is just R. This is no, it's not complex, not complex, not omega dependent. Omega dependent. Neither complex nor omega dependent. It's very easy, simple case. Depend on frequency. Doesn't voltage and current always related by the same way. So on that impedance, we are typically looking at ratio of voltage and impedance. Okay, voltage and current. That is your impedance. That's how impedance is defined. Okay, now what is impedance for a capacitor? Does anyone know? Yeah. So most of you know this. This is 1 by J omega C. Hey, the complex number J showed up. Okay. The frequency also showed up. Then the capacitance C, whatever capacitance, that showed up. And finally, the impedance of an inductor. This happens to be J omega L. Great. So most of you know this. So far, so good. Right? Omega is a number. Okay. Omega is given. This is typically radians per second. Okay, omega, this is, and let me also write that, that is important. This is an rad per second. Radians per second, that is often very important. Okay. Some space there. In radians per second. Okay. So frequency F is per second, hertz. This is radians per second. 2 pi by t. Omega is given, C is given, farad, how many farads is given. This is a complex number, you can all do that. So let's do a quick test. Now, the rule is you can treat D like R. What do I mean by that? Let's look at some quick examples. Now R1, R2. So that R equivalent is R1 plus R2. Now, some element with impedance Z1, some element with impedance 0. What is Z equivalent? The rule is that you can treat Z like R. The rule, in fact, the convenience is that you can treat Z like R. This is good. So that question is fairly easy. This is just, what is it? Z1 plus Z2. Now, instead of that, you have this. Z1, Z2 is a parallel combination. What is Z equivalent here? Yeah, so that is 1 by Z1, that is, you are referring to 1 by Z equivalent as 1 by Z1 plus 1 by Z2. That's correct. So Z1 would be or that. So you got Z1 Z2 by 1 plus Z2. Right? Yeah. So if you got this, let me give you a couple of specific cases. Equals what? Impedance of, let me write it for this one. This is ZR plus ZC. Happens to be R plus 1 by J omega C. ZR plus ZC. So this is 1 by R omega C. You could simplify this further if you want. So this is technically plus J omega RC by, you can write it that way, but this is fine. technically we'll just stop there. So notice on this stage, let me just show you one case. Because we are talking about Z equivalences only. Okay. E net 1 plus Z2 would be 1 by j omega C1 plus 1 by j omega C2. Notice your capacitors are automatically adding up in the 1 over way. Right? If you pull out the j, so you got that 1 by C1 plus 1 by C2 form here. Resistances add up. So the impedance for a capacitor automatically have the capacitance in the denominator. If you pull out the j omega as common, the net capacitance, notice series capacitance 1 by C1 plus 1 by C2. That is the impedance you are getting. So the impedance form, that is 3 impedances that we wrote, has that built-in feature. You don't have to worry about a capacitor series parallel, inductor series parallel. Impedance, it behaves like resistance, because this is at the end of the day, this is voltage by current. That's the definition of that. Okay, and you could see that series resistances will add up, parallel capacitances will add up, and then series inductances will add up. That is the kind of form they are in. This is R, this is 1 by j omega C, this is j omega L. You could also see few other things. We'll come back to this later. But if omega is 0 here, if omega is 0, denominator is 0. ZC is infinite. Capacitor doesn't allow DC current. Omega is 0, no oscillation in the current. Omega is infinity. Capacitor allows it, just like, it's almost not there. It's shorted. Omega is infinity. This term ZC is 0. Impedance is 0. No resistance for current flow. Yeah, this is shorted for all practical purposes at high frequencies. We'll also see what happens here. When omega is 0, impedance is 0. That is, now DC current, inductor is shorted. It's just a wire. If current varies, there is magnetic field, all of those effects, that is captured as j omega L. Right? If omega is infinite, impedance is infinite. Right? So resistance is now infinite for current flow. High frequencies cannot flow through. It is open. That also you could see, but we'll come to that picture a little later. So this is very powerful. This captures most of the things that you need. Okay, but for now, let's look at a few other examples. That so I suppose we did do this. Z for this. Yeah, this is fairly simple. Now this is R plus. I'm not going to write ZR plus ZL. This is R plus G omega. Let's do this. I'm color coding it, so I'm not using subscripts to make it. How about this? Yeah, this is R. Write it, this plus. It's the impedance of this. Most of you are comfortable with this, right? Two more. We did that capacitance. What is the impedance of this? So series parallel inductance, series parallel capacitance. Simplify this if you want. Okay. J omega c will get cancelled. And this will be R by plus j omega R. Will cancel with this, and there is of course j omega c will show up here. Convince that. Quickly show this. Sure, all of you agree with this. Or if you want me to show the steps clearly, let me also know. These two will get cancelled. And if I had to be slightly, consistent with the notation, fraction by this fraction, that would happen to me. Yeah, R by j omega R. This is we directly wrote it down. This shows up this way. One last thing. Suppose we started with this. We started with this. Let me write down few. impedances add up. You could further write it down that you could write it this way, but the impedances add up. Okay, now that is one part. That is your impedance. So I said, so using impedances, whatever you do with resistances, they all work. If you instead of R, if you use Z, they all work. We did as the series parallel. Voltage division, current division, all of that also works. But let's look at bridge circuit, because every year there is a question from bridge circuits. Wind up with that. Balanced AC bridges. Let's do balanced AC bridges. Likely have elements that have so the bridge is balanced, and let's say ground this and ground this. That is, I have connected these two. Okay, there is a voltage. Okay, this is a I can apply a AC voltage. It's not no more a DC thing. You have Z1, Z2, Z3, Z4. What is the balance condition? Yes, the voltage here and here will be the same balance condition. Alternating current, oscillating current. Z1 by Z2 equals Z3 by Z4. You could also write it this way. It's one and the same. Or you could write it, you can take it to this side and you can take it to the side. Z1 by Z3 equals Z2 by Z4. So this by this equals this by this, or this by this equals this by this. Either way is fine. This is equivalent. What I have written in gray is equivalent. But now, these are conditions. So the balance condition, balance condition. Okay. This is these impedances are complex. The J there is depend on omega. So the balance condition is now frequency dependent. Some frequency balance, some other frequency it could need not balance. Balance depends on omega, and this balance condition technically it's not one equation. It has a real part and an imaginary part. As two equations. As two equations. Look at it in two ways. One is real part and imaginary part should balance, or the amplitude and phase should balance. The amplitudes in the LHS should balance with the amplitude in the RHS. The phase in the LHS should match with the phase in the RHS. Or the real part in the LHS should be equal to the real part in the RHS. Imaginary part in the LHS should be imaginary part should be equal to imaginary part. Okay, so let me write it down here for clarity. Z1 by Z2, Z3 by Z4. And this shows in one side, this implies, okay, real part of Z1 by Z2 equals real part of Z3 by Z4. This appears complicated if I write it this way, but this has a now real equation and then imaginary equation. This is a complex number. So we'll have a real part and imaginary part. Same thing. This will have a real part, imaginary part, right? So there are two equations. So the real parts balance the imaginary parts. That's when a complex number is equal. Okay. I can also give you a simple example. So Z is plus JB equals 1 plus 2J. This implies A should be 1 and then B should be 2. Z complex number equals 1 plus 2J. Part of it should be equal to 1. Imaginary part of it equal to B. So this is two equations. This is one equation. A plus. This is one equation. This is another equation. There are two equations here. Be careful about it. Okay, this is what I am referring to. So imaginary part of Z1 by imaginary part of Z2 equals imaginary part of Z3 by Z4. Let me also show an example. So you could also put or you could also look at it in phase amplitude form. This is the preferred one. Preferably, you got amplitude of Z1 by Z2 equals amplitude of Z3 by Z4 and phase of that angle of Z1 by Z2. Let's say that's the angle theta. Okay, I'm putting a this refers to angle of that whole thing, okay, equals angle of the RHS. 3 by Z4 is a complex number. It's an angle that these two angles should match. Again, let me write this. So amplitudes match. Amplitudes match. And angle or phases match. If it's a sinusoidal signal, they all differ by phases. Okay, so phases match. So summary, condition is the same, but you're dealing with impedances, complex numbers. So because these are complex now, there are two equations. Although you're writing one equation, there are two equations there, and then the equation is also frequency dependent. Okay, fine. So every year there is a question from this. Here, Look at one question and we'll wind up, okay? See, notice, so most of these bridges, screen is shared, yeah. So most of these bridges for measurement of RLCQ, they are all AC bridges. So whatever we just studied, it shows up. And every year there is a question, almost every year, okay? Either there is a theory question like this one. Either there are theory questions, say what is used for what? 2023, 2020, 2022, right? So let's solve this question. For the balanced Owens bridge is this. So there is a, in one arm you have a capacitor, arm you have a capacitor, another arm resistor. This is capacitor resistor in series, resistor inductor in series. But you know how to deal with the impedances, right? So this series impedance, you know how to do this ZC plus ZR, ZR plus ZL here. You know what is ZL, what is ZC. So balance condition is the same. Z1 by Z3 is Z2 by Z4. You have four things. You have 1, 3, 2, 2, and 4. 4 is, let's write it as X. So this is X. So this by this equals this by this. Fine. So can we write it and tell me, can you answer this? So at least let me help you with this. Okay. Z1 by Z3 equals Z2 by EX. Okay. Implies Z1 is by J omega C1. Z3 is 3 plus 1 by J omega C3. This is your LHS. LHS Z2 is R2. Z4, that is ZX here, RX plus J omega LX. LHS equals RHS, but there are two equations. Can I try to quickly find out which of the four options? There are two equations there in the balance condition. Can you pick out? See, notice you get two conditions, equation 1, equation 2. So two equations, you will get two conditions. What is the balance condition? And can you try to pick out the option here? Give you 2 minutes. So which form you have to use? You have to be, sometimes you have to be, slightly, you have to quickly see the form, okay? Something that gives you the imaginary and real parts really fast. I wouldn't go to amplitude angle. I'll stick to what is the imaginary part, what is the real part. I'll try to stick with this. Okay. So you have to be somewhat smart doing this. Hey, what is the imaginary part, real part here? No. It's very hard to see. I have to do a lot. First, I have to simplify this denominator, and then simplify this. The amount of work involved in finding the real part and imaginary part is too high. If I try to simplify this and then try to simplify this imaginary, but there is always look for, can I quickly see the real and imaginary parts? And there is something to help you. This is purely imaginary, this is purely real. So anything you multiply with R2, you'll get the imaginary, this is like a constant now. R2 is a constant. If you multiply a complex number, you get the imaginary and real part fairly easily. This is constant into J. So if you multiply by a complex number, again you get a imaginary part and real part very, very soon. Okay. So that is something that you observe, and then from there you have to simplify. So in the exam, I would pause for a moment. Is there any purely imaginary part, purely real part? Multiply these two, and I multiply these two. I pause for a moment in the examination. I because that multiplication is easy, and I got my real and imaginary part separately. I have to do that. Okay, so I cross multiply. Cross multiplying, what I get is LHS. When I multiply in this is RX by J omega C1. Yes. That term would be J omega will get cancelled. J omega Lx by J omega C1. To show what is imaginary real, I have color coded. I'm retaining the color code. This is the LHS. That equals, now if we multiply in the RHS, what I will get is R2, R3. So that is purely real. R2, R3 is purely real. I multiplied the denominator real part with R2, and I take R2, multiply with the imaginary part. So the real part is equal to the real part. Yellow equals yellow, rows equals rows. So now Lx is fairly easy. R2, R3, C1. Looking at the rows, R2, R3, C1. Yeah, for Rx, now I have to compare these two. Rx will be R2, C1 by C. R2, C1 by, that is a C3. Okay, I had a C3 there. So R2, C1 by C3. I'm trying to isolate this Rx. By comparing this yellow with this yellow, I'm trying to isolate it. J omega will cancel. So Rx will be R2 by C3 into C1. Okay. And then when I look at this, I try to isolate Lx. J omega got cancelled. Anyways, this term is purely real, right? So Lx by C1 equals R2, R3. So Lx will be R2, R3 into C. So the yellow says, imaginary part says, this is R2 C1 by C3. That is your correct answer. Yeah. Be careful. Careful, yeah, that is a C3. That's correct. Be careful, because if you do it other way around, there are two equations. You're looking for two equations. You have to get them really fast. So pause for a moment. How can I get the imaginary and real part quickly? So I noticed you have to pause and notice, and then do cross multiply. Sometimes dividing LHS, finding it easy. RHS is easy. This is problem specific. You have to be. This is context dependent. Pause and strategy. Quickly strategize. This is what we do. Okay. So one, it's either theory based. They ask you to recall. They ask you to. Also simple, because balancing bridge, impedances now This question also you can technically answer. Okay. They can slightly make this advanced, but don't worry about it. If it shows up till now, if you can answer quickly, fine. This is 2 marks and it's worth it. Perhaps this is 1 mark, okay. But it's still worth it, okay. Okay. So let's stop here, and then now we are into electrical circuits. I got started with impedance. There is one more thing I'll do, okay. So I'll do you measure what is a voltmeter, what is an ammeter circuit. Those two I'll show, and then we'll now go to first order or frequency response circuit. First order, I have given some primer. This exponential decay equation is thus. Then frequency complex numbers, bare minimal primer, I also gave it today. So next week most all easy questions and circuits will be able to be. You should be able to solve easy moderate questions. Okay, hard questions, don't bother about them. But from what I know, hard questions in these subjects are rare, okay, or a minority. Okay, that's all for now. Let's stop here. Have a good one. Take care, and I'll see you again later on. Okay.